All right, so before we solve algebraically an equation, let's go quickly through the equations and the steps for problem solving. And then we do two examples, one with a horizontal motion, a car, for example, and one with a free falling motion. All right, and both of them are going to be complex motions. So here are the equations. Remember, these equations are true only if acceleration is uniform or assumed to be so. All right, very important. Here are the five equations, the most commonly that we use, and here are the involved variables. So for each equation, I listed the variables that are in the equation. So on the first one, for example, acceleration is missing, right? On the second one, final velocity is not there. On the third one, initial velocity is not there. On the fourth one, displacement is not in that relationship. And the last one, time is not there. So in order to solve an kinematics problem is to find one of the quantities. Remember the quantities, which one they are, right? So delta D, VI, VF, delta T, and acceleration, of course, DI, DF, distance, and whatnot. But these are the main one. So as you can see, there are five of them, right? And all five quantities. And all our equations have four quantities involved. So, and there are, so how do we solve an equation with respect to one quantity? We have to know the other three. So minimum, we have to know at least three quantities must be known. All right, in order to solve a problem. So let's try to solve the first one. Before we solve them, let's go through the steps. So here is usually what we do when we solve a problem. We read, all right? We understand what the question is asking us. We are able to visualize, right? If we do that, then we're good. We have to decide on the object or object that we're studying and what are the time intervals, right? If we do that, then we're good. Going back to visualizing, we have to draw a diagram, and we have to, very important, to choose a coordinate axis, right? Which means we have to be able to choose a frame of reference. And why are we doing that? Because we're going to deal with vectors, and we have to be consistent with our directions. We have to be able to figure out the given information. So remember, the given information could be implicit and could be also explicit. All right. So explicit means the numbers are there. Implicit means based on what you're reading, something is given to you. Something like, for example, at rest, or it came to a full stop, which means, or it starts from rest, which means you know initial velocity or you know final velocity. Okay. And of course, you have to figure out what is it you're looking for, what is it you're trying to find. What physics applies there, so which means, I'm dealing with kinematics or dynamics or conservation of mechanical energy, whatever that is, so you can narrow it down to what equations you're going to use, all right? So the equations are related to the physics that applies. Then you're going to solve algebraically, which means you're going to rearrange equations before plugging in numbers. All right. You do what is known as unit analysis. You check whether the equation that you came up with will it give you correct units, and that's a very helpful tool to figure out that you've done the right thing. We take care of significant digits. Remember to keep it safe, always get the lowest. All right. And then we do a rough estimate. Like, does our answer even make sense? Like, if I ask you, well, what's the speed of a runner, a human, and you find it to be 45 meters per second, that's not something that makes sense. Okay, it's not reasonable. So you have to check your numbers again. All right. And at the end, you check the units one more time, and then you report your final answer. All right. So those are the general steps for solving a physics problem. And here we go. Let's do the first one. So we have the following: determine the stopping distance for a car with an initial speed of 95 kilometers per hour and a human reaction time of 1 second. The acceleration of the car is negative 4 meters per second squared. So what we're going to do is, once we read it, we want to visualize this, right? So it says here that the car has an initial speed. So what I do is I draw a diagram just to see what's going on with my problem. So usually what I do is I draw a line showing to me the whole motion. All right. So we go from 1. So it says a reaction time of 1 second. So which means for 1 second, the car kept going with whatever was V1. It will be also V2 going with constant velocity, right? With 95 kilometers per hour before even realizing it has to stop. And then the brakes are being applied, right? So what's going to happen eventually at point 3, the car will stop. So here we're going to have a uniform accelerated motion. All right, so there you go. I visualize my problem, and I know what I have to find, right? When it says stop in distance, it means I have to find displacement, and I know what is given to me. And remember, we have to make sure the units are correct. So let's start. What is given to me, the initial, or V1, which is the same as V2, which is 95 kilometers per hour. Before I write, since I'm dealing with vectors, I have to make a choice about the direction, and I'm choosing to the right to be positive, right? So we have 95 kilometers per hour. It's 26.4 meters per second. I'm hoping you know how to change kilometers per hour to meters per second. You just divide by 3.6, the number, right? Unit analysis that you've done in grade 11. What else do we have? Well, it says that the stopping distance, right? So which means that final velocity has to be 0, right? So V3 is going to be 0 meters per second. We have that delta T, the reaction time, 1 second, right? So from 1 to 2, it took 1 second for the car to travel. And we have the acceleration. So the acceleration is negative 4 meters per second squared, which is an explicit information. As you can see, I have to report 2 significant digits. So what is that is required to me? It says the stopping distance, so which means the distance or the displacement from point 1 to point 3, all of it. What is it? All right. So there you go. I did those first steps of the problem solving. What physics do I have to deal with? Well, I'm dealing with kinematics, right? In this case. So I have to use some kinematics equations. All right, so here we go. We start writing the equations. So we have 2. This is a complex motion, right? So it's not just one type, there are 2. So from 1 to 2, we have a uniform motion, very basic and straightforward one. From 2 to 3, we have a uniform accelerated motion, right? So we start with the equation where our unknown is involved. So the displacement from 1 to 3 is the displacement from 1 to 2 when the driver is still driving at 95 kilometers per hour for that 1 second, plus the displacement from 2 to 3 when the brakes are being applied. So here's my first equation. All right. Delta D from 1 to 2 is very straightforward. It's whatever is the velocity at 1, because it's uniform velocity, times that delta t from 1 to 2. So here's my other equation. All right, and so now let's see what we know for that last part of motion. So remember, our equations are this one here, right? So we need one where we have to know at least three things about that part of the motion to be able to solve it, right? And I'm going to go back to our question now. And if you notice here, we know initial velocity, we know final velocity, and we know acceleration. So we do know three things. So we're good to go. And the equation that we choose is that v final squared, or let's put it v3 squared, is equal to v2 squared plus 2 times the acceleration times the displacement from 2 to 3, right? And now what we have to do with this equation, we have to solve for delta d from 2 to 3, right? So delta d from 2 to 3 is v final squared minus v initial squared divided by 2 times the acceleration, right? And you notice what I'm doing, I'm numbering the equations. So what we're going to do now, we're going to substitute equation 4 and 2 into equation 1, right? Because when do I decide that it's time to start substituting? Because on the right side of these two equations, I know all the variables, right? On equation number 2, v1 is 26, delta t is 1 second. In here, v3 is 0, v2 is 26, and the acceleration. So everything is known to me. So delta d from 1 to 3 is equal to v1 times delta t from 1 to 2 plus v3 squared minus v2 squared divided by 2 times the acceleration. Since v3 is actually 0, we don't have to write it in the equation, so we can make the equation a bit easier to read. v1 times delta t from 1 to 2, we can write here minus v2 squared divided by 2a. And this is my final equation. And why is this my final? Because I know everything on the right side here. So now it's time to do some unit analysis to see whether my equation stands. All right. So what does it mean, unit analysis? I see the units for the left side, right? The left side has meters, right? Because it's displacement. So I want to make sure that the right side will give me meters, right? So let's see the right side. Remember, I'm working only with units. So it's velocity, which is meters per second, times time, which is second, minus velocity squared, so it's meters per second squared, divided by 2, which has no units, and the acceleration is meters per second squared. At this point, I do what I do with regular variables. I cancel all the common variables. So the right side is meters minus meters, and of course, meters minus meters is meters, right? So which means I have the same units. So I'm good with unit analysis. I also expect a positive number, right? So I check very quickly. So because this minus here bothers me, but remember that the acceleration is negative, so I'm going to have overall a positive number. So at this time, I do numerical answer. And I have delta d from 1 to 3 is, the velocity is 26.4. So 26.4 times 1 minus 26.4 squared divided by 2 times negative 4. All right. We plug in things into our calculator. So I have 26.4 squared divided by 8, and then I have to add 26.4. I get 113.5 meters, since I have to report two significant digits. Delta D from 1 to 3 is roughly positive 100 or 1.1 times 10 to the power of 2 meters, so 110 meters, right, with two significant digits. So I'm going to go very quickly back to show you what is it I want to see on a test, all right? So on a test, I want to see a diagram, right? I want to see the given required information. I want to see the starting equations, right? And I want to see the final equation, right? If possible, that would make me very happy. I want to see the unit analysis and just the final answer, right? So everything that I didn't put a check on it, I don't really care. I don't want to see them. So if you notice, I have 1, 2, 3, 4, and 5 checks. All right. So make sure that you do that when you solve a problem. And if you're not sure, just go back to this video again. I'm just going to do an extension here. And the extension is graph. I'm just going to sketch all the graphs, right? So I'm going to sketch them. So the position time graph is the first, the first 1 second is moving at uniform motion. Remember, about 26 meters. And then it slows down to a full stop till it gets to 110 meters, right? I haven't figured out this time, but I don't have to do it. And if I were to do the acceleration time graph, again, T and A, on the first 1 second, there is no acceleration, so it's 0. And then is -4, right? And then the velocity time graph, on the first 1 second, the velocity is 26.4 meters per second, and then it slows down to a full stop, right? So there you go. Very quickly, we're able to sketch the graphs and give a beautiful solution in a decent amount of time. All right. My next question about free falling, I'm going to take it in a separate video so that I don't make the videos too long.